think it's going to be only this many of us. Mass said he's not well. And Abdullah said he has to attend the award ceremony. He had an award. Yes, I don't know what it's like.
He's getting an award.
Yes, that's what he told me. You should know. You guys should know.
He didn't answer him.
Yeah, so. I posted homework 11. 11, right? Yeah. Oh. I'm confused. That is a homework. Can you see it online?
No, I haven't looked at it.
Okay.
Homework 10 is due today.
Yes, but I posted it just now and I recall I called it homework 10.
You want to look?
Can you guys look very quickly, immediately? Is it homework 11 that is showing up?
No, it's 10.
So is there a 9, 10?
9 and 10 is there already.
Can you reload it?
I think you upload instead of this one. Homework 10. Like this.
I think I made an error. Okay, so I can do it here. Right? Sorry. I think I made a mistake.
Homework 10 was this one, now it's radiation in time.
So I just overwrote it, is it? How do you go here? So I overwrote it, correct? Okay, I'll fix that. So I deleted a homework and put something else in this. But homework 11 has been posted. It's just that you lost homework 10, but I'll change that.
Homework 10 was replaced.
Yeah, homework 10 got replaced suddenly, right? And even I called it homework 10, that's why I said 7.4. I thought I wrote it 10, yeah. So this is homework 11, so there's been some error, or until I reach back and fix it, I think it will take me an evening. So be aware of that. Is that clear? Don't be confused.
Yeah.
No,
Is this the last homework?
no,
Hopefully. No.
sorry, no. There's probably 20th, 27. So 2 more homeworks after this. So 11, 12, 13. We'll go until 13 and the midterm exam. So, and in between we have, midterm 2 is there in between, and there's a final exam. So there's a bunch. of them. But I'm not changing anything new. These homeworks are from the last year, but still you guys have to work for you guys, it's new. And even the final exam, probably I won't do it to probably. Yeah. But I did have some of the homeworks earlier, so that will be the scattering material will be new, but I think it used to be midterm, but now it will come into the exam or sort of home. Yeah. Oh, it is. Okay. That is a cursor. Yeah. Better. And we still have midterm. Or midterm 2. Midterm 2 is due on April 30. And probably will be available later tonight. I think I Yeah. Later, let me explain that.
Okay.
And it should not be very long. One. Okay. So, we started introducing radiation. Or we already introduced radiation potentials. We talked about scalar potential and vector potential, but mostly we are interested in electric and magnetic field. So we are to get the electric and magnetic field from potential. Remember, everything is very general. We are not specifying the charge and currents here. So again, let me maybe draw a diagram. So radiation fields, or radiation in general. What we have is some region of space which is denoted by R prime, and that is an observation point. Idea is that it's very far away. This is R minus R prime. And the idea is R prime is very close to the origin. You keep your origin practically inside the inside this region, and R prime is very much small compared to R. So you can have a characteristic length if you want in terms of the sources. So that's pretty much what we are saying in that approximation. Mostly what happens is R minus R prime, which plays an important role in the Green's function. This can be approximated as to leading orders. This can be approximated as the length R, since the origin is practically inside here. This length is practically R, but then we have a small correction to that, and that is R hat dotted with R prime. It's not completely captured by R. You cannot drop R prime completely. The dot product does contribute, and that's higher orders in there, but that's the approximation. That's a primary approximation in radiation fields. And yeah, so and what we showed is that so in general, we keep our sources, so rho of R prime and T prime now. Things can change with time also. We are in dynamics, and the current density, the charge density and current density are mostly inside this region. We are keeping that very general. We're not saying exactly what the charge is or what the current is. Think of, just to get a physical intuition of what we are doing, think of an antenna. Like, how does an antenna work when you have a cell phone tower? This could be your cell phone tower, and that's your cell phone. Right? Signal goes from here to there, and you would like to control that. So you're controlling, what are you controlling in the cell phone tower? Or the current, right? That's what you're controlling. In principle, you could control charge also, but mostly, at least in an antenna, it is a current that you control. At what rate you change your current, that's what affects you. But in principle, you could have a charge change with the charge density change with time also, and get similar effects. So that's what the intuition you want to keep. In your homework, you basically take a very simple situation of just one wire and then another wire. So one wire is simple, we keep two wires, right? And two wires, there's a current changing in each one of them. And remember your double slit experiment. So if you have two slits and you have a radiation, let's say light is coming in this direction, you have a fringes, right? That's your double slit experiment. And OPEX, double slit experiment. in optics. But in principle, this is satisfied by any wave character, like anything that has a wave nature. If you put in here, will give you patterns in here. In fact, you can see this with water waves, right? If you have two small openings, let's say ripple tank effect, and you oscillate the water, so create surface wave by just using a ripple tank, you see the same effect there. So if you use radiation, let's say there is an antenna here, there is another antenna here, make a simple situation there. You should, if you confine yourself to this plane, you should see a maximum. If you walk with your cell phone, for example, let's say there are two cell phone towers very close by, and you move perpendicular to that. And as you go, there should be a dip in the intensity of the signal, and it comes back, dip, comes back. And that's what you do in your homework. So look for that pattern. That's just to give you an intuition. It is described in words. There is no diagram there, but intuition is exactly that. And here we are talking about a general situation. The results that we get here will be used in your homework. Okay, so that's the situation. Okay, what's the scalar potential in general? The scalar potential in general, very general, not even radiation, more than an exact expression for it, is you have R prime and do the T prime integral. There is a T prime integral, so that's a delta function, and that's equal to rho of R prime. And instead of T prime, you replace that with a retarded time. This is what we did last time. I got at least one of the steps. Again, this is exact. This is not radiation approximation. This is exact. Similarly, A R comma T is equal to mu naught over 4 pi Q R prime. Current density R prime E minus 1 over C or minus 1 pi. Have the comparison if you were doing statics. What's your scalar potential? So there is no time then. So statics, right? If you're doing statics, there is no time in here at all. You use superposition principle, add up all the scan for all the charges around in the space, and each charge contributes, and that's charge density. You write it in terms of charge density, and it's R minus R prime. Potential due to a point charge, keep adding that up. You get the electric potential at any observation point. That's statics, that's superposition principle. But it's exactly the same superposition principle that is coming in here, except that you have to take care of the retardation. Right? It's not the charge density at the time t you're worried about. It is at a certain distance beyond, and this distance is dependent on where your charge is. If a charge is farther, then the retardation is farther. Right? So it very quickly complicates it very much. For example, if you have 3 friends, one friend is living in Chicago, another friend is living in New York City, and your third friend is living in London, and if you guys have to meet at a certain point, your friends have to start from that places at different times. The closest friend can reach in 6 hours. New York City, assuming that they all drive, let us say they have to come, London cannot drive, right? Let's say it's farther, right? At least the distances are significantly different. They all have to come to Chicago and then take a train. So you see that if you're coordinating the times, then you're worried about the distances. And that's the retardation we are talking about. And very quickly it can get complicated. And we are write down all, take care of all those considerations at a very generic level. We are trying to make it very general. Of course, at a very minute level, you can always do backward and get it, but we want some general fundamental relations, and that's what makes it challenging. Okay, so that's your potentials. So these are potentials, very exact in a sense, no approximation done. But the moment you say it's radiation potentials, what's the difference that comes in? So radiation potentials now, this is exact. So radiation potential is when you're very far away from where the source is, and phi of RT then is equal to, you can replace this with R minus so on. And that's equal to, that makes it very simple. You have 1 over R that comes out, and the cube R prime, and charge density is now at T minus R over C, observation point alone, and plus R hat started with R prime over C. And similarly, the vector potential is equal to mu naught over 4 pi 1 over R, and instead of charge density, we have current density evaluated at T minus R over C plus R hat R prime over C. It's convenient to call this the retarded time. This is the retarded time, so this is all a time. So how far is this retarded time? Again, notice this retarded time is R prime dependent. Where you are, where the source is, it matters. So if there are 3 sources, one in Chicago, one in New York, and one in London, then each one of them has a different retarded time. So retarded time depends on where the source is. So that's our dependence. Questions? Comments? Okay, so we have what is retarded. We have defined what is a retarded time. And that's T of R is equal to T minus R plus R hat prime over C.
This potential, we are defining it as radiation potential when the observer is far away than the source.
When the observer is very far away from the source. In fact, it will turn out that the way we write it, it is independent of R. Right, so or all the R dependence will be in this.
Oh.
And to the extent that we are talking about at the, like, think of the universe, we have a dome. Like when you look at the stars, for example, for our purposes, stars are just points on a dome. It doesn't matter how far, you never see the distance, how far the star is. One of the stars you might be seeing might be 100 times farther than another star that you, for example, Jupiter is much closer than the star Sirius. That's the name of a star. One is 1 light year away, and one is only in kilometers, like 10⁹ kilometers. But when you look at it, both are 2 points, right? So they are on the dome that you can think of. So think of a sphere at the boundary of our universe, that's a sphere of infinite radius, and you're only interested in the angle. So mostly we will be talking about angle. All the distance dependence is captured in this.
Why don't the inside the row like independent?
We will see that. So at this point, you will say that, oh, no, that's not correct. There is an R dependence in here, right? True. As it sits, there is an R dependence there. But remember, when we did this, we neglected order R square, right?
Yeah.
So we want to be consistent. So every time we do this, we want to drop things out. If I have dropped it here, I have to drop it everywhere, right? So even here, I have to drop it. But I'm not interested in the potential, I'm interested in the field. And when I'm doing the field, this contributes. So that's why I'm keeping it here, so that in the next equation that I write, I don't have to redo the calculation. So this will start contributing in a minute when I do take the derivative. And at that time, I can delete things, I can get rid of things if I want to. Does that answer your question? Yes. So it does show up here. That's what we're working with the retarded time. remember electric field, if I want the fields, I have to take the gradient, right? So I have to take the derivative here, and when I take the derivative, I worry about where my R is, and that's your R. Right? There's R here, or there's R there, even though I'm interested in on the dome, but at least the derivatives I have to worry about. Right? Same thing with the magnetic field is the cross. So I'm foreseeing the fact that when I take the derivative, I'll be hitting inside this. So for once and for all, let me take the derivative and finish it off. Like this is a digression if you want. Let's take the derivative of the retarded time. So let's take just as a exercise, let's take the divergence, not divergence, right? Gradient of the retarded time. This is with respect to R, it hits your this point here and the R hat. So this is minus gradient of R times 1 over C plus gradient of R hat divided with R prime over C. I think we started on this last time. This is nothing but R hat, so that's minus R hat over C. Remember, gradient of the magnitude is R hat, and gradient of the vector R is 1, right? The dyadic 1, if you want. That's R hat over C plus. There's more information here, so I have to do gradient. So this is R hat is not there in this, right? So I have to write R hat as R over R. Then I know how to operate. Or if you know what that answer is, that's good enough. But in terms of this, you want to write it as R over R. Use that or expand that out, R hat over C plus. This can hit the numerator or the denominator. When it hits the numerator, it's vector R over R. And then when it hits the denominator, it is minus 1 over R square. And eventually it hits R again, right? So there is vector R, gradient minus 1 over R square, and then gradient of R. If that makes sense. Dotted with vector R prime. Is that clear for this? There was a chain rule I do. Now I use this, that's 1, and this is R hat. So that's the same as minus R hat over C plus this is 1 over R, and this is R hat over R square, but there's a, I write this also as R hat. So this is R hat over R dotted with vector R prime. Good. Process this a little more, just for or it's good to see what this means. I mean, yeah, so when you say there is 1 minus R hat, it's good to have an interpretation for that. 1 is basically a complete set. That means any vector in all 3 directions. I think of all, take any orthogonal basis, and there are 3 directions associated with that. I'm subtracting the R hat out of it. That means whatever this piece is, it will not have a radial component. I've removed the radial component. So it is all tangent. Think of a dome, right? When I'm thinking of the dome, 1 minus R hat is a projection operator, which is along the dome. Direction is along the dome. Angle theta hat and phi hat, like 2 directions on the dome. That's what this means. Remember, 1 could be R hat, plus theta hat, plus phi hat, if you remember here. And then I'm subtracting this R hat, so that goes away. And then I'm left out with theta hat plus phi hat prime, which is a complete set on the dome, on the surface of the dome. So whatever this is on the surface of the dome. That's the way to interpret that. That's an advantage of writing it as 1 minus r hat r. But it's also good to think of it as a vector product. So let's see what that is. So let's see plus 1 over r, and this is vector r hat prime, 1 dotted with this, and this is minus r hat dotted with r prime. What is the quantity inside the parenthesis? Does anyone recognize that? Oh, there's a C I missed, probably. That was C, right? C, let's see. Something in the parent, whatever you see in the parenthesis is a familiar quantity. Any recognition there? And again, that's a feature that comes out of this. This is a cross product. So it is 1 over r times, let's see, so this is r hat crossed with r hat crossed with r prime. Is that correct? So the first one, so this is minus, right? You use your back cab rule. So first vector is r hat, so that's your r hat, and then these two dotted. And the second is along r prime, but r hat dotted with r hat is 1, so that's this. So that's a back cab rule. But again, if you think of it as a cross product has this feature that it will start with a direction, give any direction if you want, and if you want it in there, right? So think of any vector you want, let's say m, and then or in this case it is r prime, right? R prime. So this is r prime, and that's r hat, let's say. R hat dotted with r prime is coming out of the code. So this is r hat dotted with r prime, but then it depends on the angle theta. Correct. But now you take the cross product of that with respect to r prime again, and now it is perpendicular to that. So this two directions will always, this is this down here, right? This is r hat crossed with r prime, and this is r hat crossed with. So the three directions are, so always, right? R hat is a unit vector. R hat, pick any vector, r prime, independent of what r prime is, any vector, right? R prime, and r hat crossed with r prime. This is always an orthogonal set. R hat was this way, like this is r hat. R hat crossed with r prime is coming out perpendicular to that. These three always form an orthogonal set. You don't always have to pick your ijk. Give me any vector with reference to that r hat, you can always create an orthogonal set. Those are all details. It is handy when you're working on this, but those are all just comments if you want. All that plays a relevant role in the concepts, but for our purposes, this is just a that's an identity related to gradient of the retarded time. I can also take the gradient prime, that means the gradient with respect to vector r prime of T of r. That's equal to, this means I'm hitting the r prime, that is down here. So that's equal to plus gradient prime of vector r prime dotted with r hat over c. right? It hits only this R prime there. That is one, right? In the prime coordinates one, and that's nothing but R hat over C. Clear? So that's the two identities we will need as we are when we are actually operating all this gradient and time derivatives. Any questions until here? Some motivation clear?
Can you explain the last thing?
Oh, T of R depends on T, R, and R prime. Right. I took the gradient with respect to R, right? This is with respect to R. Like gradient is d by dr, right?
Yeah.
There's a d by dr prime also. So d by dr prime will hit this.
Oh,
Right? It won't touch this, it won't touch that. So this is all zero. When it hits that, I rewrote that in the opposite order, like dot product A dot B is the same as B dotted A in electrodynamics, unless you're doing quantum mechanics, you can do that interchange. And this one is the identity again, right? Or the dyadic here. One dotted with R hat, and then you get a hat. So that's a simple identity you have. So your two identities, one is gradient of the retarded time, and the other is a gradient with respect to the prime coordinate or the source coordinates. Gives you R hat over C. Or both have this R hat over C, but one is plus and one is minus in a sense. Right? So that's a crucial point. It will turn out that this is a second order term, at least in some of the calculation. Okay, so we want to calculate. So let's first do this, right? Gradient of phi. Let's do gradient of phi of RT in the radiation of zone, and radiation zone, the potential is given by this. So I have to see where all it hits. So first of all, it can hit 1 over R. So that's gradient of 1 over R. And dq R prime, and that's rho of R prime. And let me call that P of R. And I can also hit the gradient on T of R itself, correct? So I use the chain rule now. So this is plus 1 over 4 pi epsilon naught. 1 over R, I keep it intact, and d cube R prime, I have to do the chain rule. So I say dtr over dr, which is a gradient, right? R. And then d by dtr of rho of R prime ur. Is that clear? Basically do a chain rule. So that's how I penetrate into the function. And that requires my gradient of, so this is gradient, right? This is nothing but gradient of d of R. That I already have. That I've already calculated that. That's fine as R hat over C. Okay. That's equal to gradient of 1 over R is minus R hat. So this is 1 over 4 pi epsilon naught R hat over R square d cube R prime rho of prime u R plus 1 over 4 pi epsilon naught 1 over R d cube R prime, and the gradient of T of R is minus R hat over C, and then there is this cross product, right? So it is minus of R hat cross with R hat cross with R prime over R and C. And this is d by ETR. That's it. That's. I made an argument in the earlier lecture that we are interested in fields that go as 1/r at the dome. Like by dome, I mean at a very far distance away in the radiation zone, right? I would like a 1/r surviving there so that when I multiply it with the flux, when I'm calculating the flux, that is an area that depends on r square that cancels out when you're thinking of the energy. So it is a 1/r I'm interested in, and accordingly, these approximations were made with that. So I want to keep 1/r or at least have the dominant part in here. So this is order 1/r square. Okay, this term is order 1/r square. Okay. Oh, we didn't move it, is that? Oh. You guys like watching there. Is it because of the angle or is it because it is better resolution there? Both.
For me, it is convenient there.
It's because of the direction or is it because of the resolution?
Sometimes this one disturbs my.
Oh, this one.
Yeah.
Okay, that's okay. But anyway, okay, so this is 1/r square. Notice this is r hat. So this is order 1/r. There's an r here, vector r, this is r prime, so this is order 1/r square again. Okay. So this is weaker, if you go very far away, if you're on the dome, this is weaker, these two are weaker than this. And if you think of it, if it is 10⁻�3, if this is 10⁻�3, this is 10⁻�6, you won't even capture it in the next 3 decimals. Right, so in the radiation approximation, you can neglect these two over this. So you need only this piece. Okay, that's the crucial part. That piece is actually independent of r prime because this is r hat. That can come out of the integral. So overall, what you've done is, no, not this. So this is the minus sign that comes out. So I have minus 1/c. 1/4 pi epsilon naught. And there is an r hat dotted with r. We're talking about the gradient of the potential, which is like electric field. It's a contribution to the electric field. R hat over r. And then integrate over the volume. But now notice what contributes, it is the derivative of the charge. If the charge alone sits, doesn't matter. You have to move the charge, it has to move, right? It is the derivative that comes in, and this is d by dtr. So let me write that as t prime of rho prime and t prime evaluated at t prime equal to t of r. This is the same thing as this, but it is emphasizing that this is evaluated at the retarded time. It's the same. You can write it in this form if you want to. Let's go. Okay.
You said the order of 1/r
Yes.
squared, it's because
I'm taking the dominant term. If you want, I'm taking the dominant term. And why am I doing this? Because I'm interested in the radiation zone, very far away.
but if we add the integration, that has r to 3.
This is mostly, this is r prime, remember. I'm r. This is r, right? Observation point r. R prime, you don't have to worry. R prime is all in this region. It's very small, tiny. So I don't worry about r prime. I'm only interested in r. I have to somehow, because that's the large part. So I have to put that in the denominator, and here it's 1/r square. You know, the r. And did I answer your questions? Right. Okay. Any other questions? So the dominant piece in the radiation approximation comes by the change in the charge density. Like if you don't change it with time, you won't get radiation. So if a charge is just sitting there, nothing happens. But it has to change its charge density for it to play a role. And it turns out that it will be the acceleration of that contributes eventually. So that's another feature. We will see that as Larmor's formula. But here now we have a gradient of phi. But electric field is not just this, right? It has to get contribution from A and with B also. Let's do B because B is again, as far as the operation goes, it's just gradient. It's just we have to put a cross product. And then, so the whole calculation works for A also. So notice what is gradient operator on A. I'm not putting the operation cross there. Until I don't put the cross multiplication or the cross product, everything goes through. The same calculation that will go through, same arguments. So I can write this will be -1 over C. It's mu naught over 4 pi there for A, R hat over R, and instead of rho, this will be J. Two vectors now, right? This is d by dt prime times J, now current density. And again, evaluate it at T prime is equal to T of R. And there's going to be cross product. If I were to take a cross product here, or to take a cross product there. Otherwise, it's exactly that expression. So I immediately know the magnetic field. If I know this curl, I know the magnetic field now. What is the magnetic field in the radiation zone? B of RT. I just have to take the cross product and I'll write the C here that floats around on to the left. And that is equal to, that's just for convenience. C is put on the other side. And then take a cross product, right? So this is going to be equal to, let me write this as R hat outside. So this is minus R hat crossed with mu naught over 4 pi times 1 over R and Q R prime d by dt prime of the current. Think of the antenna. This is the current in the antenna, right? That's what decides your radiation. Let's define this. This has a dimension of current in it. Let's define this to be. So let's define this to be I, the vector I.
So
Yeah.
can you realize the curl is going to be in that place by looking at the
Yeah, right. I put it in between here, right?
Yes.
So I will put it in between here. Remember this gradient, if it was a curl, so this is a vector now, it has to be here, right? So this is the term that we are interested in. So it will be, so this R hat and this will be J. So you have to follow it through, but it will turn out that it will be cross. If you are confused, just go through it, put the cross and do it again. Right, so that's the only way. If you're, the moment you're confused, just do it. It's only 3 steps, just do it. But I'm saying that it will be exactly coming in there, but probably not necessarily obvious all the time. Like in this case, it is clear like this. If there's a confusion, just read it. Okay, let me call this I just temporarily, or it is actually is that remember magnetic field is created by a current, and so, or maybe actually I should call it C times I, so that's not completely because I multiply by C, so there's also a C, it's multiplied by C in there. So this comes out to be equal to I'm going to write the R hat on the other side. So this is mu naught C over 4 pi. And that is a vector I crossed with R hat over R.
Minus,
Is that correct?
what's the minus?
Because I switched, right?
Oh,
I had cross with.
I think it what's I,
Some definition.
okay,
It's
what is
just-
I?
I choose I because I think it has the dimensions of the current. Let me check, but I don't think I have defined it here. In your homework, I defined more, by any chance, if I'm missing. Let's check this, how about this, let's check this, right? So this is volume, so this is length cube. Right, length cube, 1 over time, current. Density is, this is J, right? So J is Q times V, right? So that's charge, Q times V, which is length. Oh, what happened? Yeah, length over time, yeah, and J per unit volume, length Q. Right, that's all there is to it. And let's see if all this comes out correct. Length cancels out, so yeah, so this is current times velocity, right? So this is current times velocity, I give that C, so it's just a redefinition. But the idea is that there is current, and that's the main point you want to keep in mind, because the magnetic field that's created by this current in your antenna, it is I that decides that. R is just there because you're very far away, it will cancel out. Because you're on the infinite dome, that when you take the flux, it will cancel out. You'll always talk about per unit area, and that will go out. That's not important. It's only the I that decides the current, at what rate you, the arrangement of your antenna, right? Whether it is two parallel bars or two, it's a triangular bar, all that changes the what kind of radiation comes in. Like the design of that antenna matters, but otherwise distance, it's not that. Right? And what exactly is your time dependence, that decides. Like at what rate are you doing that? That matters. But otherwise, it's all that. What is mu naught times C? Right? It's good to think of what is mu naught times C. What is 1 over epsilon naught times mu naught? Right? That's speed of light. And that's how much? 299979245 a perfect integer meters per second. Right? It is a perfect integer. Why is it a perfect integer? Because we chose it. Like recently, this was done only very recently, since 2006, it's a perfect integer. All the time it was always measured, speed of light was always measured. But now there are three quantities, epsilon naught, mu naught, and C. So somewhere you have to fix, this was earlier, these two used to be fixed earlier, before Maxwell came in. These two was fixed and this was derived out of that. But more recently, in 2006, the committees decided that why make these two independent? You make this independent, you have to fix it to some value. So you made it an integer, perfect integer, and then this is derived. So one of them is measured again, and then that's right. But that's not the point. What about mu naught C? We always say this quantity, mu naught C is the other ratio. This is nothing but mu naught over epsilon naught, right? And how much is this? What are these? What is the unit of this by any chance?
Resistivity.
Resistance, it's resistance, right? This has the unit of resistance. And then the question comes, what is this? And it depends on whether I take the 4 pi or not. I think if I do not take the 4 pi, probably it is 25. Check on this. Okay, so check. I think it's 25 ohms. But then the question comes, this is a resistance of what? right? Vacuum is like vacuum doesn't have any resistance, right? You cannot think of a resistance for vacuum. If you connect to probes, that's no resistance like that. And 25 ohms is a pretty large resistance. Okay, this is usually called the impedance of vacuum. In the sense that when you think about radiation, like radiation, it's not, the system always tries to oppose, remember Faraday law. This is the impedance that is exerted against what you're trying to do. And this shows up later also, this has connections with when you make this a quantum feature, there are connections you make to this, but it is good to recognize at this point that this is of course one quantity you can construct, but this is another quantity you can build out of these constants. We don't emphasize on that, and this will come in your homework again. Always the radiation is in terms of this constant. Think of that as resistance. So there's a current, there is a resistance, I times R, that's a voltage, right? So that's is this the dimension of voltage? This is the dimension of electric field, but there is a distance here. Distance times electric field is the voltage. So voltage, current, resistance, right? This is resistance. Current, resistance, R times the electric field, that's a voltage. V is equal to IR, like antenna. The moment you talk about antenna, you're talking in terms of electric quantities. V is equal to IR shows up there, at least dimensionally. Okay, that's the magnetic field though. Now that was easy because just one operation gave it. For electric field, we have to do one more, and that's the time dependence in here. So that's a time dependence with respect to A. That's actually easier because it only sees the T in it, and the only place where T comes is in the retarded time is T. So it's sort of easy. So it is mu naught over 4 pi dq or J. This is d by dt of R prime and J of R prime. So this is the retarded time. I take the derivative with T. So when I take the derivative with T, it is the same as taking the derivative with T of R. It is the same. So I write this as T prime, and evaluate it at T prime as equal to T of R. Because it is linear, whether I take the derivative with T of R or T, it's the same. Since it is just a constant multiplied by that. Oh, so if I have this and if I have this quantity near, I'm prepared to calculate the electric field. Magnetic field we already have. Okay, so I can save some.
Oh, I think that impedance vacuum is
Other again?
377.
377, that's including the 4 pi. So divide it out by 4 pi. Can you divide that by 4 pi now? It's approximately 6. Oh, so 377 you said, right?
Yeah, 377.
So 377 divided by 4 into 3, that's 12. Like that's 377 is approximately 400 divided by 12,
Yeah.
right? So that's 12, 3, right? It's not showing up. Not good, right? Maybe it's 2 pi. Okay, divided by 6. So 377. That's 3, right? Quiz, right? Evaluate mu naught C over 4 pi. And then yeah.
What is
What's the question?
377?
How is 377 and 25 related? What's the division, right? So let's say 400 divided by 25. So that's 4 into 4, 16. Correct. 16 is first one. No. Okay, forget the value of 25. Maybe I was remembering it wrong. Yes, whatever this value is, I always thought it is 20. Maybe that is the temperature, right? Oh. Yeah, maybe. Yeah, I think I'm wrong. So that's whatever you're saying is the correct value. So it's 377, and at the most, I can get rid of the 4 pi if you want to. I think I might be mixing up the KT. KT is 25.
Oh, no, because 377 is just the square root of u not over epsilon.
Yeah, so that's the correct value.
Yeah.
Okay, so that's
So we still gotta do by 4 pi.
so if you divide it by 4 pi, you will get 16. Correct. Yeah. But let me proceed, okay, so that I can reach the complete this today, okay? So the quiz is to calculate mu naught C over 4 pi as a number. Okay, get the number, and it's there in your homework also. So it'll show. Okay, so I'm interested in the electric field. Electric field at R of T is equal to negative of this quantity. Negative makes it a positive. So that's your, oh, yeah, this one, right? So that's a positive 1 over 4 pi epsilon naught. And there is a C. So that's R hat over R and dq or prime, and then there is a 1 over C d by dt prime of rho evaluated at Q prime is equal to T of R, and there's one more term which is really a negative term, it's minus mu naught over over 5. I think so. Oh, there was a 1 over R here, right? That was damaged. 1 over R dq R prime d by dt prime and j R prime t prime evaluated t prime is equal to t R. That seems like more work, too much work to calculate the electric field, but it's going to simplify. This seems very handy, right? So magnetic field came out just in terms of current or the current that we defined, but it will turn out that this is also very closely related, and that is the following. So you have this. So we're going to replace this. I want to write everything in terms of current, because think of again antenna. Antenna is described pretty much in terms of the current density in that. So let's start with this and process this integral. Remember your conservation of charge, that's equal to the flux of the current density or the flux of charge density and plus the time variation of the charge density is equal to 0 because charge is not created or destroyed, right? That's charge conservation. That's charge conservation. With me? But I'm interested in R prime and T prime, and especially T prime being a retarded time. So I should be careful with the retarded time. First of all, let me just change one simple thing. Let's do prime. Everything is prime. That's an immediate thing that doesn't change anything. But now I am interested in evaluating this at the retarded time. So notice what is happening. So I evaluate this at the retarded time. So that's straightforward because I'm taking a derivative at T prime. It doesn't matter. I'm doing it. This is the only place where it gets. But on the right hand side, this is as a catch in here, so technically speaking, first day. Notice what the language, first take the divergence. With respect to prime coordinates. And then replace. P prime is equal to T of R. That's the language. But I somehow want to. Not do this here, somehow I want to operate this after taking the divergence. So that I can do an integral over it. When I take the integration. The divergence theorem works, but divergence theorem wants the divergence outside, right? So let's try to see if this is okay or not. Is this okay to say that this is primed dotted with J or prime, comma, T of R? Is that okay to do that? Okay, so the question is it okay to substitute this there? Oh. So you can redo it, reconnect, I suppose.